Thanks for all those who came along to my the keynote earlier on. I have made some improvements to my setup, so hopefully now you're able to see my screen and my video. Um, uh, I had to. There's some things involving network cables I do not want to go into because the sysadmin in me wants to cry about the setup that is being jury-rigged here to make all of this work. But hopefully I'm coming across loud and clear, and that you're enjoying this, probably self-isolating at home. We're now going to be talking a bit about microservices and how they relate to the concept of serverless. Serverless is a big hyped topic, and I think rightly so, actually. And we're going to be exploring a little bit about what serverless is, but talking about serverless and specifically function as a service in the context of microservice architectures. As before, we will be using Slido for questions. So if you want to go and ask a question during the talk, you can go along to Slido and use the hashtag Y860. That's Y860, and that will allow you to ask questions as we go. If you want to, go to that website now, open it up in a window, so you can keep it open, you can keep it refreshing, and just ask questions as we go through the session, and that will give me a lot of things to answer when we end. I'm not going to talk about the work I do and the books I've written because I did that in the keynote. But if you want to know more about, decomposing monoliths to microservices and all that sort of stuff, you can find information about all of that and my books and the services that I offer through my company over on my website. But we're here to talk about serverless and microservices, so we should talk a little bit about microservices as I always draw them, these nice hexagonal architectures and kind of, your microservices have become almost ubiquitous in terms of for many people it's unfortunately become the default way of building software, but it's uppermost in our minds. But I do think it's often important to just refresh the most important characteristics of microservice architectures. And we talk about these things as being independently deployable services that work together, modeled around a business domain. So we're taking business functionality, we're packaging it up together, and then we're exposing that business functionality over networked interfaces. So we're typically talking about one process talking to another process over some sort of network boundary, although that kind of blurs a bit when we start moving into the world of functions. But we use the business domain to define those service boundaries. But the really important characteristic here is this idea of independent deployability. And that's a really important facet. So many of the things that we look to get from microservice architectures, and I would say potentially the key benefit that we get with microservice architectures over other styles of modular architecture is this idea of independent deployability. So we can make a change to a service, we can deploy that service into a production environment without necessarily having impact on the rest of the wider system. This can make it easier for teams to work in isolation or more improving autonomy of teams. So your team can work on your service by itself, they can make decisions about when to deploy. This also works really well when you're trying to get teams to own more of the end-to-end sort of operational responsibility for your software. Hopefully this also means is that you can have more developers working on a problem without getting in each other's ways. So if you could sort of break apart the different parts of your overall product or the overall system, give those to different teams to own and manage. If their services are also created in a microservice style, they can be changed and evolved independently from each other. And that's a really important idea. And then this idea of autonomy cut through a lot of what we're looking at for microservice architectures. James Lewis, who was one of these sort of early people looking into microservices, he wrote the original article over at Martin Fowler's website. He said that microservices are an architecture which optimize for autonomy. And so by picking a microservice architecture, we're sort of saying that autonomy is really important to us. And so we're going to pick microservices because hopefully it's going to allow us to go faster, work more in parallel, etc., etc. And this idea of sort of empowering teams and allowing teams to own more responsibility, it cuts across a lot of the shifts we've seen in IT development over the last 20 years. If you think about the public cloud, for example, I touched on this in my keynote, a big part of the public cloud is about allowing direct self-service access. So rather than having to raise a ticket to an operations team and say, please, can I have a machine? Instead, you could go to your own dashboard and click a button and get it, or even better, write some code, or use some sort of automated scripts to spin up the machines that you want. And so public clouds have been incredibly useful in terms of further empowering teams and giving them more autonomy. And autonomy here largely through the ability to self-service. Some other benefits as well that come with the public cloud, as we touched on in the keynote. And really, when you get down to what the public cloud is, it's a succession of higher, multiple abstractions over underlying physical infrastructure. You think about the core sort of infrastructural building blocks of storage, compute, networking. Rather than actually dealing with the physical aspects of that, we're working with abstractions that allow us that are virtualized abstractions. And so we're dealing with things at a slightly higher level. I don't have to go and connect a network cable. I could run a for loop to connect 10, 20, or a million virtual network connections. And at the base level, when we first public cloud first came out, well, that's actually not true. But what really caught the imagination of public cloud early on was really quite, the grand scheme of things, low-level abstractions over these three primitives of storage, compute, and networking. We used to talk about the cloud using these four letters, IaaS, infrastructure as a service. So that was the term used to describe what AWS were offering, which again, as I think was a bit of a misunderstanding, but nonetheless, it's a term that's still in some widespread use. Infrastructure as a service is really talking about those cloud abstractions that sort of are quite close to the physical counterpart, right? We can imagine when I connect an attached storage device that's like plugging a disk into a machine, or when I open up a network connection between two machines, it's like plugging a cable in potentially. So the analogies between those two things are quite similar. And of course, we've gone from, in this world, when we talk about compute in the space of infrastructure as a service, what we're normally talking about when I'm spinning up a machine, what I'm actually doing is I'm spinning up a virtual machine that's sitting on top of physical infrastructure. And so the cloud provider, I call an API to say spin up an EC2 instance on AWS, for example. In the scenes, what's actually happening is, that API call is hitting a virtualization layer running on their physical infrastructure, and it's spinning up a virtual machine for me. It's handling all the networking and then passing control over to me. And to be honest with you, from a functionality point of view, is quite similar to what you could experience something like VMware, albeit with a nicer control plane on top. So that's sort of infrastructure as a service and sort of quite low level. And then we started getting a bit sort of looking at other types of abstractions, and containers have become a big part of the landscape. Certainly for people building sort of systems on top of Linux-based operating systems, containers have been around for many, many years. And Windows is actually, the story around containers and Windows environment has been getting a lot better. Since really 2000 and with Windows Server 2016, containers have been supported much better within the Windows ecosystem. Although there's still definitely work to be done in terms of the size of those containers, because even with things like nano server and stuff, we're still looking at quite large containers in the Windows ecosystem compared to the Linux ecosystem. But where we are, it's an improving game. But now many people are thinking about the container as our unit of deployment, which is a slightly higher level abstraction than on a virtual machine, right? We're dealing with something else now. We're sort of dealing with a package of our operating system and our application together, and that's now our unit of deployment. Whereas before, I would bring up a virtual machine, have to apply the configuration for that virtual machine's operating system, then I'd put my software on top, then I'd configure that, and then it was deployed. And now we've kind of got a single unit. And part of the container metaphor sort of has more subsequently has become this idea that you can treat a container like a black box. It has a common interface to work with that container, but just like shipping containers, you don't actually have to care too much about what's going on inside. So I'm deploying containers, but I don't really care if one of them is implemented in Java, another's implemented in Ruby, another's implemented in C#. And of course, I could be having different operating systems running inside those containers. As long as my container platform lets me run those types of containers on it, I shouldn't actually care about what's happening inside that container. So from the point of view of a deployment activity, I'm sort of further abstracted from the detail. I'm not having to get deep in and configure a virtual machine to run my software. I'm just being given a container and I'm going splat. There is a container. I've dropped it on the system. And this is quite useful, with a shipping container. All shipping containers, as a common standard shipping containers, they have the same fixing points, they have the same dimensions. And what that means is you can have a common set of tools around managing those containers. You can have a common palette for it like this that can take that's built, designed to take any container. That container could contain grain, it could contain a car, it could contain a bunch of washing machines, or maybe it's empty. You can even get refrigerated containers that sit within the same space. And so by having a common container format, we also can have a common set of tools. And this is really what Docker did for us. Before Docker, we had containers in the Linux and Unix operating systems, but we didn't have that common packaging construct. And that's what Docker gave us. It said, well, this is how we should package. This is the image we have for a container. And here's like a common set of tools we can use to manage these containers. And although many people now run containers without using Docker, they kind of set the standard in terms of what that format should look like and how we should work with that. So we've gone from, say, physical infrastructure to virtual infrastructure to infrastructure as a service, having a nice API control plane. We've then gone a bit above that, and we're now thinking about containers as a way to build and manage and ship our productions. But then when you start looking at the world of the cloud, there are just so many options in terms of how you might want to go about deploying and however you might want to go about managing things. And it can become a bit overwhelming. So I'm going to take you, through a few examples of how we think about deploying and managing it. So if I was in the world of, say, just purely Docker, and I wasn't worried about all this Kubernetes stuff, but I just wanted containers, maybe I would spin up a virtual machine, maybe an EC2 instance, and I would run the Docker engine on it. So the Docker engine is going to manage the isolation between these, and actually manage provisioning these containers and manage the isolation of those containers. And so I could spin up multiple instances of my service. Each instance of my service or different services could be running in different containers, all running on that same machine. In this case, this could be a virtual machine. So I could take a physical machine, break it into virtual machines. I could then take a virtual machine and break that up into lots of containers. And those containers, from a resource point of view, are quite isolated. So I can say, okay, this container has this much memory and this much of a CPU. The isolation isn't as strong as, say, virtual machine isolation, but it's still really quite good. I also get this property of uniform deployment. This is what Docker gave us, was managing containers on a single machine. But of course, we want more than one machine. We might need more than one machine to run our platform because we want to handle more scale, or because we need to handle the failure. If one of our VMs dies or one of our physical machines dies, we need to make sure we've still got enough instances to serve the traffic from our customers. And so there were lots of different solutions that came out in this space for managing containers across multiple machines. But the one that has very much won, of course, has been Kubernetes. So Kubernetes gives you a way of managing effectively container-based applications across multiple machines. And one of the things it does really nicely is this thing called desired state management. So with desired state management, you can say something like, I've got a service. I want to make sure there's at least 5 instances of this service running across all of the machines I have. And if one of those instances dies, Kubernetes will spin up another one for you. If one of the machines underneath that dies, Kubernetes will also rebalance where your services are running. And that's a really, really powerful idea. And again, sort of this is another more high level abstraction. Rather than having to worry about an individual container, Kubernetes is just saying, well, look, I'll deal with all the hassle of where they're going to run for you. You don't have to worry about that. You just tell me how many you want and how big they should be, and I'll sort the rest for you. And you see the sort of inexorable march. This is the story of computing, right? Developers, we're always looking for more powerful abstractions, because as we create better abstractions, we get to do more work, right? We get to do more things with our time. It makes us more powerful, because rather than having to deal all the time with a low level detail, I can abstract away that detail instead, work at a higher level and get more done. Many of us, I suspect most of us, do not code in machine code anymore, nor do we code in assembly code. We use higher order programming languages, because that turns out to be much more effective for most software development. There are sometimes cases where you do want to go quite low level, but most of the time you're very happy working at the level of sort of general purpose programming languages. And the same is true for how we think about working with our infrastructure and with our sort of cloud or cloud-based resource. We might want to go quite low level, but a lot of the time we're happy being higher up. And Kubernetes gives us a more highly abstracted platform for working with containers. But when you look at really containers, you say, well, okay, with virtual machines, I take a physical machine, I break it up into virtual machines, and those virtual machines allow me to sort of have separate isolated execution units on the same physical machine. Well, containers sort of do the same thing in a way, and you could argue that containers are just a maybe a better from a developer point of view form of virtualization. We've basically found a way of breaking apart a set of resources into isolated sets of resources that can be pegged to certain processes. So maybe, if you look at it, I mean, although containers are often much better from us from a developer point of view, they can be much more cost effective because they're not as heavyweight as virtual machines. They allow us to run those containers on our laptops more easily than we might be able to with, say, VMs and things like that. Arguably, they are just a different type of virtualization from that point of view, but maybe a more useful one. So let's talk a bit about serverless. And serverless, the term serverless has actually been around for a lot longer than people think. The original sort of definition of serverless, as far as I've been able to tell, and I've asked lots of other people about this, and we've all come up with the same answer, actually comes from an article by Ken From. And so Ken wrote the piece about the sort of where he saw the future of software and applications going, and he talked about it as being serverless. And he actually wrote this article back in 2012, which is sort of interesting. So he said the phrase serverless doesn't mean that servers are no longer involved. It simply means that developers no longer have to think that much about them. And what he was reflecting on here was a whole host of services and products that sort of abstract away from developers the concept of the underlying infrastructure. We don't have to work at a computer level anymore. We're working at some higher level of abstraction. And so there is this, so serverless is talking really about an observer, right? The observer, the people who use serverless software, they see it as having no servers effectively. That's us as developers. If you're running this on premise, of course, a serverless stack of some sort, your developers in-house might see it as serverless, even though you as an operations team might have to manage those computers, of course. Now, this was articles written in 2012, but what seems to have happened is that people have reduced the concept of serverless to just meaning functions, function as a service. And they're saying, well, when people say serverless, what they're actually talking about is function as a service. And that's, I think it's unfortunate because I think that really misses the point of serverless. Serverless is not just about function as a service. It's about much more than that. So we've got, yes, function as a service, which we're going to explore in a bit more detail in a moment, but it also encompasses database as a service platforms. Think about something like Cosmos DB or DynamoDB. You're not worried about the machine or how many machines you have. You are basically sort of operating in a pay-as-you-go environment. You're just creating tables and letting the platform underneath that work out all the details. You're abstracted away from the underlying servers. It also includes things like storage. Take a look at something like AWS's S3. All you do with S3 is a blob store service, you just throw data in. You stick it in a bucket, you have a hard, you maybe have some structures to that bucket, but you don't have to worry about allocating disks. You don't say, oh, please add another 1 terabyte disk to that. You just throw the data in and you're charged for what you use. We also have messaging products. The very first service launched by AWS was SQS in 2006. SQS is a serverless queue-based messaging product. You don't have to manage it. You just put stuff in, it comes out. That's a serverless product offering. Their second ever product offering was AWS S3, also launched in 2006. That was also serverless. So although we came to see AWS as pushing infrastructure as a service, the very first things they launched are very much things that fit the model of serverless. So it's almost this idea that maybe the future arrived a bit earlier than we were ready for. But there are many more things. When you look at those cloud-based services and those cloud offerings, there are lots of different things that fit that model. If we look at specifically AWS, which I know a bit better than Azure, DynamoDB, that's a backend as a service. Amazon S3, that's blob store service. And of course, for cloud functions, we have AWS Lambda. So AWS Lambda is sort of the first of what we think of now as the cloud function platforms that was launched. That was launched in 2014. So that was 2 years after Ken came up with the term serverless. So when we were talking about serverless, there was no function as a service concept really in widespread use. So this idea that now FaaS is what all serverless is sort of also doubly not true. But we can think about the serverless product offerings like Lambda, like DynamoDB, like Cosmos DB, like Azure Cloud Functions. We can think about them as just another in the step of our, another layer of abstractions in how we work with underlying physical resources. So we can work if we want to with the underlying physical machines, but then we start to virtualize that infrastructure. So virtualizing the compute network and storage building blocks. This is where you're using VMware or using the managed VMs maybe on your public cloud providers. And then we built higher level abstractions on top of that. We created sort of container orchestration as a service systems like Kubernetes, or maybe we're using managed relational database services. Like on AWS, for example, I can spin up RDS, which is a relational database service. And although I'm sort of scaling it to an extent by a machine, I say I want a machine this big, it's actually handling a lot of the management of that machine for me. So again, it's a higher level abstraction over the management of that database. And then on top of that, we've now got even higher level abstracted services. We've got the function as a service platforms, the backend as a service platforms, those messaging products I talked about. I mean, think about the Azure Event Hub, right? That is a serverless messaging product. I've hidden even more of the detail away from me. And I think it's arguable, that we sort of also have platform as a service stuff that sits on top of this, things that give you even less control maybe, but hide even more of the detail away from what you're able to do. So as we go up these layers of abstractions, we reduce the amount of overhead that we have from a point of view of operational management. But as we come down these layers, you have a lot more low-level access and a lot greater control over how the system works. So if I have direct access to the physical machine, I have a huge amount of control over how things are done. But I've got a lot more work. And so whenever I work with teams on these sorts of things, it's like we have to find the happy place. Ideally, you want to give away as much as possible, right? And do as little work as you can. But can you cede that control? And I think often people can give up more control than they realized. And so when looking at all this picture, I sort of came to realize that I sort of think of containers as like a better virtualization, but I feel that serverless and what serverless has done is really started, well, I don't think we're entirely there yet, but what we really have done is we've created better abstractions, like better, more developer-friendly abstractions. So, maybe where containerization is a better form of virtualization, I think the serverless products we're seeing are a better form of abstraction. They kind of better developer-friendly abstractions that hide away the operational work that's needed. Now, I said very clearly that serverless isn't just FaaS, but function as a service is one of the most interesting features of product sets under the serverless banner. And I think it's important to explore that a bit. And especially as what we're going to come to is looking at these function concepts in the context of microservices. So the way sort of FaaS works is sort of one level quite straightforward, right? You've got a developer creates a function. And so a function could be as simple as something that's called raise invoice. It could just be one method if you wanted to, or in practice, it might be a bit more than that. And you then deploy that onto a FaaS platform. So this could be cloud functions, this could be Lambda, whatever else. What you then do is you can configure that function to run based on some event. So they generically talk about an event, and an event could be a file being delivered in a certain bucket. It could be a HTTP request coming in over an API gateway. It could be a message being received, message broker, whatever. So as these events come in, the FaaS platform will dynamically spin up an instance of your function to serve that request. And you're not having to configure the host. So you're not having to say, I want 5 machines that have got this much CPU, that have this kind of IO profile. Actually, all you can really do, configure with these things is you say, my function when it runs needs this much memory, and that's it. And the FaaS platform without you being involved, says, a request has come in, about to launch a function, here's a function to serve that request. And that's done all without you having to be involved whatsoever. You only pay for what's running. So if you have, say, a virtual machine running 24/7, you've got to pay for 24/7 costs. With a function, you only pay if the function is invoked. If it's not invoked, you don't pay. And so this can actually lead to making some significant cost savings. I mean, there's some variables around that, but if you've got a system that maybe is only used for 2 or 3 hours a day, you could deploy it as a FaaS platform. You don't have to worry about turning the machine off and on again, like a lot of people do. So a lot of people, if they say only going to use a machine from 9 till 5, they'll turn it off at 8:30 in the morning. They'll turn that machine off at 5:30 in the evening. Then maybe they can automate that, but it's a bit of housekeeping you've got to do. With a function as a service platform, you don't have to worry about that. If no calls are made, nothing gets launched. If nothing gets launched, you don't get charged. That's a really nice idea. The other thing is it's going to handle scale for you as well. It's going to have scale up and scale down. As you get more requests coming in, it will automatically spin up more instances. And you can limit how many instances you allow, because of course that can have a cost implication. But finally, you kind of get a property, right? If an instance dies, another request will launch a new instance anyway. It will scale up as it needs to. And kind of importantly, as that traffic goes away, it will shut those nodes down for you when they're not needed anymore. FaaS, typically these functions are designed to be short-lived. So originally you had quite short durations for these things. I want to say with Lambda, it might have been like 5 seconds or 30 seconds or something like that. You're now up to sort of, on the different platforms vary, but sort of 15 minutes can be for some of these, but you'd have to look at your exact cloud platform to know how long they run for. But they are designed to be things that kind of react to something, do the job, and then shut down again. So you're not looking for long-lived processes. So if you do need much longer-lived processing, function as a service probably isn't the right fit for you. Under the hood, the way these platforms are working is with containers. So when a call comes in to launch your function, what the FaaS platform is doing is spinning up a container instance, running your function on it. You don't have to deal with the container that's hidden away. All you do is you give the FaaS platform your code, and it deals with all that work for you. And that's a really great thing. Again, it's a more high level abstraction. The container's great, but can we design it in such a way that the developer doesn't need to worry about that container? Let's hide that detail from them. That's exactly what FaaS does. It allows a developer to just focus on code, and the operational work is done by the platform itself. Now, I have mentioned some of the constraints. You typically have a restricted execution time. You also do have somewhat limited runtime choices. Now, this does vary. With the execution time varies from platform to platform. Google Cloud, for example, is really behind in a number of runtime choices. You've got JavaScript and you've got Go, and I think Java might be in beta. I'm not even sure the other two. I'm not even sure if the Python stuff is out of beta yet. Either. Azure's actually got the broadest offering in terms of different runtimes. Theoretically, you can run a Windows bat file, as in a Windows batch file, as a function. I mean, you shouldn't, but you can. You can also run things like PowerShell scripts and functions too, which can actually be quite useful for sort of maintenance administration tasks. And AWS is doing pretty well as well, but I'd say Azure's got its broadest set of runtime choices at the moment. You also obviously have a lot less control. It's not just that you can't pick a programming language. You have to stick to the programming languages that are supported, but you may actually only have control over you might only have access to a certain number of versions of a runtime, for example. So if you've got a function that wants to run Java 5, you're probably, that's not going to work. You're going to have to be running Java 6 or Java 8 or something like that. So you also really have from an operational point of view. So from a sort of, the only thing you really get to control is what code gets run, how it gets, what causes that code to get run, and how much memory does my function have. And that's kind of it. You can't do anything to configure the underlying operating system or anything else. And also, these functions are typically considered to be pretty much stateless. So that means that an event happens, I launch my function, I do some work, and that function vanishes again. When another invocation comes in, and that a function gets launched again, you can't share any state from the previous function invocation unless you've offloaded that state to something like a database. So you can't be holding state in memory. And this also kind of means that, so we should treat these functions as being almost entirely stateless. It's not totally true though, because there are a couple of exceptions to this. We'll come back to that a bit later on, but in general, you should think about functions as being entirely stateless, which also, by the way, drastically simplifies your programming models. It makes your life much happier if you can stick to a stateless model for programming anyway. Now, coming back to microservices for a minute, we need to talk a little bit about the concept of data ownership, because this is going to apply in terms of how we start thinking about functions like that. Now, one of the things we want with functions is we want this, with microservices, is this idea of independent deployability. So we have this idea that a service owns its own data management. And so if another service wants to get information, if a service, so the customer service here wants to get data from the invoicing service, rather than reaching straight into its database, instead you go and access that data via some sort of well-defined interface. And the reason we want to do this is because we want to have very clear, explicit service interfaces that we maintain compatibility of, so that we can make changes to the invoice service safely. So if I want to maybe make a change to invoicing, I want to deploy it, I want to know that that service interface is still compatible between my releases. If I allow people to directly access my database and directly access my data storage, it then becomes a bit of a problem. Can I change how that data storage is done? Can I rename a column? Can I add a new constraint? And the answer is you're kind of not sure anymore, because you might break that other consumer. And so we talk about effectively viewing a microservice like a big black box, right? How the data is stored and managed is a hidden internal implementation concern. So we don't want these sorts of that backdoor access. And I want you to hold that thought in the back of your head when we start thinking about how we move into the world of functions. So, we tend to think of a microservice like as a collection of business functionality hosted on a network endpoint. And often we package this up as a process. We put that process into a container and we launch it. So I guess the first question is, how do I map from a service to functions? Now, actually, in a lot of situations, you can just map them one-to-one. But it does depend on how big your service is. But for services that might only do a small number of things, mapping all of your function code, your code into a single function, actually is a very, very good starting point and can work absolutely fine. If you want to go finer grained than that, and that might be a common thing, is you might start to see, well, actually, I'm going to break all the things that my invoicing service does down into a series of functions. Well, then the kind of question is, well, how do you find what things or what mechanisms do you use to identify which functions you should create? Should I have 100 functions? Should I have 1,000 functions? Do I take each method in my service and make each method a function in its own right? And no, you don't want to do that. You don't want to have tens of thousands of these functions unless you've got a real need. If you do decide you want to go finer grained than one service to one function, the piece of advice I'd give is to start looking for how you work and manage your sort of aggregates or your bits of data. So and that's an initial starting point, would be to map all the functionality about managing a single aggregate to being one function, initially at least. So inside my invoicing service, we might work with and manage, say, an invoice aggregate, an account aggregate, an order aggregate. So these sort of represent things with identity, things with state, and these also things tend to have life cycle associated with them. And if you look at your service, there's probably lots of things that are aggregates that you might manage within a service boundary. And so if you want to start mapping these into functions, a good place to start is say, well, actually, what I'm going to do is I'm going to take all the code for managing an invoice, and I'm going to create a function for managing that invoice aggregate. And so any calls related to changing that invoice get handled by my function. And this is where the word function kind of gets a bit amorphous, because all really you've got with these things, when we talk about deploying a function, what you're doing is really deploying a package of code, and you have one of those functions, which is your entry point for execution. So when your HTTP thing gets called, it's going to hit a function in the top of your function bundle, that function could call other functions. So there's no reason why you couldn't have one single entry point for all invoicing functionality, for example, and handle the whole life cycle around invoicing the single function boundary. By keeping all of the code associated with managing a single aggregate in a single function, it becomes much easier to make sure you're properly implementing the state machine around that aggregate. And so if I had 3 aggregates here, maybe if I want to go finer grained, I may be looking initially at my invoicing service now actually consisting of 3 separate functions that are now. So now I'm getting into finer grained deployment. So now I can update and change how the order side of the invoicing is done and just deploy that function by itself, which is kind of useful. Now, if you're moving from, say, deploying your service as sort of one big unit to now moving it towards lots of little functions, you also have to give sort of due thought to what's happening for people outside of your service boundary. And my advice here would be that if you're deciding to break your service down into smaller functions, that you still try to hide that from the outside world. So from the point of view of your consumers, they think they're still talking to an invoicing service. But behind the scenes, what actually happens when these calls come in is they're just being dispatched to these individual functions. So from the outside world, they think a single invoicing microservice exists. From an internal implementation detail point of view, though, you're implementing that invoicing service in terms of lots of little functions. And that's sort of, you want to hide that implementation detail because you might change your mind about how these functions are deployed. You might decide, you know what, I don't want to have 20 functions. I want to go back to 1, or I want to get rid of functions and go back to this as a container on Kubernetes. And if you've kept the external interface the same, you can do that safely without impacting your kind of customers and well, not your customers, your team consumers, which are nearly always going to be your own colleagues who are calling your service from something else. So that's good. That talks about the outside world. But what about, what about the database, right? So if I've broken my invoicing service down into, say, 3 functions for managing 3 different aggregates, or I've broken it down even further, maybe I've broken down each state transition into a separate function, which is what you can do if you take it to the extreme degree, then, well, how does that work in terms of accessing my data in my database? Because we sort of said before that we don't want lots of things accessing the same database because that causes coupling. This is something we've got to consider because one service could suddenly result in 3, 5, 10, 15, 20 functions. And all of those functions are sort of all accessing the same database. So that starts to look a little bit like having lots of services talking to the same database. We said we didn't want to do that because that creates coupling between the functions. And the reality is, if you're breaking functions down to be individual state transitions on an aggregate, then those functions are inherently coupled anyway. So the way I tend to try and think about this is I say, look, these functions implement this service. So these 5, 10, 15, 20 functions, they all implement the invoicing service. The invoicing service manages a set of data. And so as long as you kind of have that idea of that logical association between the functions and the service, then you can still have this working quite happily, right? So you can kind of think of now, rather than one service owning the data, now you've got a logical set of functions which implement the service, which own the same data. So my invoicing service, which consists of lots of functions, still can all access the same set of data because they are kind of seen conceptually as the whole thing. They're worked by the same team, for example. If you start seeing that different people are working on different functions a lot, that might give you cause to want to try and pull those functions out of the invoicing service per se. And you might also want to pull that data out as well. Now, where these things get confusing in the world of serverless, of course, is that the databases in this world are a little bit different. When we think about a relational database, we have, well, typically with a relational database, we have the idea of a schema. So one relational database instance can support multiple different logically isolated database schemas. So I can have, my invoicing schema as all of my invoicing data is inside that invoicing schema. and I can control who accesses that invoicing schema, and that invoicing schema is owned by me, the invoicing service. And so that kind of idea of that sort of logically isolated data set is kind of really useful in the world of relational databases, and other non-relational databases too. But when you start looking at the world of serverless databases, those abstractions aren't necessarily there, and there's just so many more options, right? So when I'm thinking about Azure, I've got table storage, I've got Cosmos DB. On Google Cloud, I've got Bigtable, I've got Spanner, I've got Data Store. On AWS, I've got Simple DB, I've got DB, I've got Aurora Serverless, and these are just a subset of the serverless data store option, sort of database options out there, right? These are just the first, 8 I could find. Now, in reality, the list is a bit shorter than that because no one uses table storage or simple DB anymore. But it's there's still a lot of options out there. So you're going to have to pick if you want a serverless database, or actually kind of having that nice property of not having to manage the detail. You're going to have to work and assess these different options out there. Aurora Serverless is quite different to DynamoDB. Aurora Serverless on AWS is much more akin to a relational database than DynamoDB is. DynamoDB looks a lot more like sort of a document database. It's closer to a document database like Mongo, I would say, as is Cosmos. Cosmos and DynamoDB are kind of a similar looking databases. And so these databases have those some different characteristics. So on DynamoDB, for example, on Cosmos DB, I don't have the concept of a schema with a set of tables in it that can be locked down. What I actually have is I have a table. Now, these tables in DynamoDB and Cosmos DB aren't like a table in a relational data store. They're much more like they're basically, you can imagine like a JSON document, right? But you can have multiple nested columns inside it. And so often you don't need multiple tables to store your data. You might get away with storing all of it in one table that has sort of a bit more complexity around it. So here's my invoicing functions using stuff from the invoicing table. And I've also got a customer table over here. And my issue invoice function needs invoicing data and it needs customer data. Okay, so I've got a customer table, I've got an invoicing table, that's fine. Okay, but I've also got some stuff for managing customers, and they need to talk to the customer table, and it starts to look a bit like messy, right? It starts to look like we could be getting back in the world of everybody accessing everybody else's data. Because remember, we still want this idea of sort of logically isolating our different service boundaries. So here, what I've got is, say, team A looks after the invoicing service, and team B looks after the customer service, and the customer service manages that customer data. This issues function shouldn't be directly accessing somebody else's data. That's not what we want, right? Because this is just as bad as one service reaching into another service's database. The key thing here is, though, that these different tables are on this, if you've created them both on the same account, they're both available. You can just go read them. You can go view them if you want to. What you actually have to do is you have to yourself put in place that idea of the sort of schema type abstraction over the top of it. Because what we really want to do is say, okay, well, what I've got is my black box, which is my invoicing functionality, and my black box, which is my customer functionality. And if I want to go between those black boxes, rather than going through the direct access to somebody else's table, I still should go to a function. So I shouldn't, if I need the customer data, I might go and use the appropriate function to access that customer data. Now, the challenge is, because we lack this logical abstraction of the schema with things like DynamoDB and Cosmos DB, limiting access is something that you end up kind of doing either at the account level or using access roles. So you could actually create an access role for the invoice service, which can only see the invoicing table, or an access role for the customer service that can only see the customer table. So I've done this before by using effectively prefixes on table names and applying that as part of the identity and access management rules. So this role, the invoicing role, can see all DynamoDB tables that start with the prefix invoice hyphen. And then that way you can kind of get some level of grouping. That's a bit of work you have to do yourself to create those abstractions on top of that. I did say earlier that these functions are typically stateless. That's sort of not quite true. There's AWS have a thing called step functions. Now, step functions don't really let you have functions themselves which have state, but it does allow you to pass state from one function to another. If you look at how step functions work, you basically kind of create designs, maybe the wrong word, but step functions gives you a way of sort of sequencing a whole bunch of Lambda functions that get executed in a certain order. When one function finishes, it passes the state on to the next function. This looks a lot like a workflow management tool or BPM. I'm actually a bigger fan of Azure durable functions, which I think is a much smarter, developer-friendly approach. Whereas step functions often as you end up wading through huge amounts of JSON to coordinate multiple functions working together. With durable functions, it basically hooks into reactive extensions. So I have a piece of C# code, and I could say, okay, well, I want to go and execute another function now. So I can go and say, I'm going to do an async await on this other function invocation. And what happens when that async await executes is that your function gets suspended. It executes the other function. Once the other function is completed, it comes back, it starts your function up again, and the results of that are passed back to you. So it's sort of stateful, but the word stateful is sort of is an interesting. It sort of has very specific meaning. What's actually happening beneath the hood, if you've ever looked at things like continuations, that's basically how the durable function stuff is working. It's really, really interesting. Now, at the moment, I think it's only officially supported for C# on Azure, but Microsoft has said that they are going to roll out durable function support for all the languages they support. So I think the Java durable function stuff is in beta at the moment. So it's well worth looking at if you're looking to build more complex flows. And I like the idea of keeping that stuff in code rather than sort of having to push it out to some sort of separate JSON type structure, because it becomes harder to see how things hang together. Whereas with durable functions, you've actually got half a chance of like actually following the code flow and the flow between those functions within the scope of just by sort of walking through your code. I've mostly so far been talking about on-premise, public cloud-based services, and the reality is that the serverless offerings are amazing in public cloud and are very, very, very poor on private cloud. Part of that is because a bunch of the things that the serverless products do behind the scenes is just working with things that are difficult, right? Like lots of file servers and all these sorts of things. So we don't really have something as good as Amazon S3 that runs on premise, because the initial outlays and costs are just enormous, right? You don't get to say, I'm just going to store a gigabyte in a blob store. I only want to pay 10 cents an hour, because step one in implementing an on-premise blob store, involves giving a 7-figure check to NetApp for a big Philo or SAN to sit somewhere in your data center. So there's some challenges there. But for something like function as a service, there are open source frameworks out there to give you FaaS-like capabilities. You can look at something like OpenFaaS, for example, which is a framework that you run on top of Kubernetes that can give you that sort of function invocation type experience. It's not as fully featured as the FaaS platforms that exist on Azure or on AWS, but it's still a good approximation of that. We've also seen Google are moving towards this thing called Knative, and so Knative is going to embrace this idea of FaaS type implementations and other types of service products that you could run on top of any Kubernetes platform. The idea being you could go from Kubernetes platform to Kubernetes platform and have access to some common serverless type offerings. The one caveat I would say about Knative is that it's quite early on in its evolution. Google have decided to take Knative private in terms of its evolution. They're not developing that specification in the open like they did with Kubernetes. They're going to own that, then drive that themselves. And Google's sort of track record in kind of getting technology to a point where it's stable enough for use, as in you're not getting lots of churn and change, hasn't been great. It took a long time for Kubernetes to stabilize. Istio is still not stabilized, and Knative is being built on top of Istio. So maybe Knative will be the future. I don't really think it's going to be the present for many of us, just because even if maybe it works now, they might quite completely redesign it in 6 months from now, and we'd have to expect that to happen. Now, if you're interested in playing around with any of this stuff, I think if you want to see the sort of really appreciate how powerful function as a service can be, I think just spend half a day playing around with it. Pick a cloud platform of your choice, and start working with it. Now, the out of the box experience for setting up functions on these things is a lot worse than it should be, and that's why I tend to point people towards a tool like the serverless framework. So the serverless framework gives you a really nice command line interface for packaging your software, deploying it onto these cloud platforms, executing them from your, from actually your terminal. You can pull down the logs, you can roll back versions and everything. It's a really, really nice tool chain for working with function as a service on, sort of AWS cloud, Google Cloud, or Azure. Theoretically, it's platform agnostic, right? So the command line is kind of platform agnostic. So you almost don't care from a command line point of view if you're talking to Amazon or Azure for your function. But the reality is it's not as simple as saying I can just dynamically run those functions at either place. There's a bit more configuration than that. But it is well worth a look. And I think that the nice thing about the serverless framework is also it supports lots of different programming languages. Some of these sorts of serverless SDKs out there are specific to certain platforms. Like you get ones that are just for Node functions, you get ones that are just for Python functions. You can go straight to the underlying cloud platforms. You can go and use their consoles and stuff to do your stuff with their graphical user tools. I would urge you to start with the serverless framework just initially, because what you do is you can configure your function using a bit of code. You can have it checked in. You can fully automate your function creation, deployment, management, and development life cycles from the beginning. And that workflow is just so nice. It's definitely worth taking a look at the serverless framework. Spend 2 hours at some point this week or over the weekend, create a couple of functions, play around with them, and you'll just start to get a sense of just how awesome they can be from a developer point of view. So just to summarize, if we think about serverless, we should put serverless in the context of this continuing drive towards having more and more powerful abstractions, creating higher and higher order abstractions over underlying infrastructure that allows us as developers to get more stuff done. I think the current crop of serverless offerings may not be the future. I think there are better things to come. I don't think they've really delivered on the full promises of this stuff yet, but they are well worth exploring. For many of the organizations I'm chatting to who are looking to move to the cloud, I'm suggesting, maybe rather than trying to Kubernetify your application, maybe you actually start looking to see if some of this stuff could be functions instead, and just go straight to a native FaaS platform. It can open up some significant benefits. I mean, above all the serverless stuff is by abstracting away more and more detail from me, it's empowering me more as a developer to get more things done myself, which in turn is going to help this drive towards independent deployability. So in summary, think of serverless like more developer-friendly abstractions. It's allowing us to do more, to sort of own more responsibility without having to do more work. It's making us more productive as a result. Functions can map really nicely to microservice boundaries. You can start thinking of your a function. You can have a one-to-one mapping from a microservice to a single function. If you want to break it down further, you can go from the aggregate to function. If you want to go even further again, you can go from the state transitions of an aggregate down to a function as well. But just if you're going to do all these, if you're going to start having lots of functions, still have this overall arching idea of a collection of functions that work closely together and keeping data ownership within that sort of logical service boundary. I've got a bunch more stuff on serverless over my website. I've got a video I did for O'Reilly that you can watch as part of their online learning platform. I've also got other talks on this stuff over on my website as well, which is easy to find on the internet. But thanks so much for listening along. We've been having questions open on Slido, so I'm just going to spin that up on my iPad. It's trying to do Face ID, but I've got my headset on, so it's getting confused. So let's just see if we've got any questions that have come in on Slido. I'm just going to open that up again and refresh that. So while I'm opening up Slido, this is a chance for you to ask any questions. I know there's a little bit of a delay. 860. Okay, let's take a quick look. There we go. So there's a good question here from Marek. So Marek says, I didn't catch you say much about performance. Taking containers up and down sounds like a lot of overhead, especially in cascades of east-west calls. So what Marek is talking about really here is what some people have described as a cold spin up. So a request comes in and I have to launch a container to serve the request coming in. Now, the time taken to cold start a container like that could be quite long, relatively speaking. If you're working in a programming language like Java or C Sharp, the nature of those runtimes mean they have a bit of a longer ramp up time. If you're working with something like Python, Node.js, Go, they spin up much, much faster. So how quickly a cold spin up occurs is going to vary from runtime to runtime. So if you have to have very, very fast spin up times, that's something you might need to take into account. The other thing is that the underlying FaaS platforms are going through huge amounts of optimizations to keep that cold spin up time as low as possible. They're doing lots of things about sort of optimizing things like the JVM and the CLR to improve those spin up times. You might look into things like the Firecracker VMs and stuff like that that Amazon are doing to make those things that container invocation even faster. The third thing that's going on here is it's very rare you actually get a cold spin up. So what actually happens, is certainly I know this happens on AWS, I'm less sure about how it works on Azure, is Amazon actually keeps a sort of live copy of your container it keeps it around. So although it's not executing, once a function stops executing, it leaves that container where it is, but it's in a dormant state. And so when another execution comes in, they divert it to an already launched container instance. I said it's like it shuts down again because from the point of view of the function does shut down again. It does vanish. You don't have any state between those functions, but actually the runtime that held that function can be kept hold of by the underlying cloud platform. And so actually they might keep that around for hours. And so it's very rare that you'll see a full cold spin up time. If you want to see more, let me just check. So what you might want to do is to take a look. I'm just taking a look. Yeah, it's some really interesting posts out there. I can certainly see. Let me just put a link on the cloud share. So if the thing I'm going to search for is cold startup time or cold start time. There is an article I read a while ago that might be a bit out of date. And this is AWS specific, but it goes a little bit into some of the detail around these spin up times. So you might be interested in reading this article on how AWS does it. So this is actually somebody from the outside in trying to look at how long those things are kept live for. It also talks about the link between memory size and spin up, because that's the other thing. The other thing aspects around performance is you can sometimes see a bit of variation in performance. When you give a function a smaller amount of memory, so like 128, 256 megs, what you'll often see is Amazon will actually, and I assume AWS does the same, Azure does the same. So AWS says, okay, well, I'm going to give you at least 256 meg, and that's also a proxy for how much of a CPU you get. But if there's more performance available to you, they'll let you use extra capacity. So what you'll see is with the smaller function sizes, you'll see a bit of variability in how quickly those functions execute. Whereas actually, if you want guaranteed fast throughput, you're often better picking a larger memory size as well. And that tends to relate to the underlying machine having better IO. So but the only level of control you have is that actual memory footprint. The person to follow on this for AWS anyway is Yan Sui, who's there. So Yan's also the Burning Monk online. This is actually one of his blog posts. He's done so much work in this space for AWS. I'm sure you'll find other in the Microsoft world. I'm sure there are some great MVPs out there that can help share knowledge with you about how this works on Azure. But I hope that makes sense. And this is something I talk about in more detail on that O'Reilly clause. Okay, now let's see. Have I still got my sliders up? Okay, I was going to see if there's any other questions. Okay, so I think I've got all the questions done. I appreciate that. I hope the line's been good enough for you, and you've been able to hear me. If you've got any other questions for me, best thing to do in the real conference, you could grab me in the corridor and we could have a chat. We can't do that here, so I would say, Jess, just ping me on Twitter. I'm just at Sam Newman on Twitter, and as I said, there's a whole load of information about all the kinds of the work I do, and books and all sorts of other things over on my website. So I hope you'll find something of interest to you, and I hope you enjoy the rest of your day.